In today's video, we look at the fundamental theorem of calculus. Now, what this theorem does is it relates the Riemann integral that was studied at the very beginning of integration to antiderivatives, which we just finished studying. This will allow us to calculate any integral without the use of Riemann sums. Before we can introduce the fundamental theorem of calculus, we need another result first, and this is known as the mean value theorem for integrals. And what this theorem says, if f of x is continuous over an interval a to b, then there is at least one value c that is in AB such that f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. This value is known as the average value, or the mean value of the function, and will be studied in more depth in a Calculus 2 series. To prove this, we note that since f of x is continuous on a to b, the extreme value theorem says it'll take on both a minimum and a maximum. Within this interval, right? Call these values little m and big M respectively. Thus, for all x in this interval, little m will be less than or equal to f of x, less than or equal to big M, right? That's the definition of minimum and maximum values. So what we now have is if we integrate both, not both sides, if we integrate every term of this inequality from a to b, right, the inequality will hold, right? That is by one of the comparison theorems. And it is extremely easy to show that if we take the integral from a to b of just dx, it is just the length of that interval, so b minus a. That is really simple to show. That means that this left-handmost integral is m times b minus a, and this right-handmost interval is big M times b minus a. Now all we need to do is divide everything through by 1 over b minus a. We get little m is less than or equal to 1 over b minus a times the integral from a to b, f of x dx, which is less than or equal to big M. But this integral, the 1 over b minus a times the integral from a to b of f of x dx, is just a number. and it is between little m and big M. And f of x is continuous. And takes on all values. Between little m and big M. The intermediate value theorem says that there must exist a point C within A to B such that f of C is 1 over b minus a times the integral from a to b of f of x dx. That is what we wanted to prove, so we've now established the mean value theorem for integrals. We can now introduce the fundamental theorem of calculus. And there are actually two parts to the fundamental theorem. Part 1 says if f of x is continuous over an interval a to b, and big F of x is defined by big F of x is equal to the integral from a to x of little f of t dt, then big F prime of x is equal to little f of x over the interval a to b. Part 2 is typically the part that people refer to when they're referring to the fundamental theorem of calculus, and it says if little f is continuous over the interval a to b, and big F is any antiderivative of little f, then the integral from a to b of f of x dx is big F of b minus big F of a. So what the second part says is to evaluate an integral from a to b. First, find any antiderivative of the function, then evaluate that antiderivative from a to b, meaning you evaluate it at b and subtract the evaluation at a. Right? Proof of part 1. We obviously define big F of x as the integral from a to x of little f of t dt. What we're going to do is we're going to use the limit definition. That is, big F prime of x is equal to the limit as h approaches 0, big F of x plus h minus f of x all over h. Now plugging in how f of x is defined, we get 1 over h times the integral from a to x plus h f of t dt minus the integral from a to x of f of t dt. Using properties of integration, we can write that second integral as plus the integral from x to a f of t dt. Again, using properties of integration, we can now write that sum as the integral from x to x plus h f of t dt. But that is just the average value. Right? So 1 over h times the integral from x to x plus h is the average value of f over the interval x to x plus h. So the mean value theorem says that there has to exist a point C within that interval such that f of c is equal to 1 over h times the integral of x to x plus h f of t dt. Also notice, as h approaches 0, c must approach x, right? Because as h is approaching 0, this is shrinking to just the interval x, which means c would have to start to approach x. Since f of x is continuous, the limit as h approaches 0 of f of c, which is now the limit as c approaches x of f of c, is simply f of x. We can now put all of this together. F prime was the limit as h approaches 0, 1 over h times the integral from x to x plus h f of t dt, which is the limit as h approaches 0 of f of c, which is f of x, which is what we wanted. And so part 1 of the fundamental theorem has now been established. We now look at proving part 2. To do this, we let P be a partition of points x sub I. Okay, for I equals 0, 1, 2, up to some value big N. More specifically, this is going to be a regular partition. Of the interval a to b. Then what we can do is we can write big F of b minus big F of a is actually big F of x sub n minus big F of x naught. And we can write this as f of x sub n minus f of x sub n minus 1 plus f of x sub n minus 1 minus f of x sub n minus 2 plus, keep going until we get to plus f of x1 minus f of x naught. But this is the sum I equals 1 to n f of x sub I minus f of x sub I minus 1 Now, since f is an antiderivative, so big F is an antiderivative of little f over a to b, mean value theorem suggests that for I equal to 0, 1, 2, up through n, there must exist a c sub I within the interval x sub I minus 1 to x sub I, such that f of x sub I minus f of x sub I minus 1 is equal to f prime of c sub I times x sub I minus x sub I minus 1. But this is equal to little f of c sub I times delta x. Right, so this piece here was the mean value theorem. This piece here is using the fact that big F is an antiderivative. If we substitute this in, we find that f of b minus f of a is now equal to the sum I equals 1 to n, f of c sub I delta x. But that is a Riemann sum. So if we take the limit as n approaches infinity of both sides, this is just a constant. And the limit of a constant is the constant specifically. So that side remains f of b minus f of a. But now the Riemann sum will go to the integral from a to b, f of x dx. That is exactly the result we wanted, and so we have now established part 2 of the fundamental theorem. Now with the fundamental theorem proven, we can introduce one last topic, and that is if we consider an integral of this form. Now, we've already seen that the antiderivative is big F of g of x plus a constant, where big F is an antiderivative of little f. Right, that was from the change of variable video. Now, the fundamental theorem of calculus, FTC, says that the integral from a to b, f of g of x times g prime of x dx will equal big F of g of b minus big F of g of a. If we use substitution equals g of x, we will get this result. Let u equal g of x and let g prime of x be continuous over an interval a to b. And let little f of x be continuous over the range of g of x. Then the integral from a to b, f of g of x times g prime of x is equal to the integral from g of a to g of b f of u du. This is applying change of variables to definite integrals. We now look at several examples. What we're going to do is first find d dx of f of x, where f of x is equal to the integral from 1 to root x sine of t dt. This is obviously an application of part 1. Now, what we need to do, though, is part 1 was a to x, not a to root x. So we say, let u of x be the square root of x. And notice then that du would be a half, or I'm sorry, 1 over 2 root x. Right? Then we can write f of x as the integral from 1 to u sine of t dt. This means that f prime of x would equal sine of u times du, the derivative of u. All right, so that would be sine of the square root of x all over 2 times the square root of x. Looking at another application of part 1, we're going to do the same thing, d dx of f of x, where f of x is equal to the integral from x to 2x of t cubed dt. First, let's go ahead and write f of x as a sum of two integrals, x to 0 plus 0 to 2x. And then we can write this as the integral from 0 to 2x of t cubed minus 0 to x of t cubed. Now the second integral already fits the form for part 1 of the fundamental theorem. For the second, we're going to say let u be 2x. U prime would be 2. And so we can write f of x now as the integral from 0 to u of t cubed dt minus the integral from 0 to x of t cubed dt, which means that f prime of x is u cubed times u prime minus x cubed. This equals 8x cubed times 2 minus x cubed, which is 15x cubed. We will now start looking at part 2. So we wish to evaluate the integral from negative 2 to 2, t squared minus 4 dt. Fundamental theorem of calculus says the first thing we need to do is find any antiderivative. Well, power rule says t squared will be t to the 2 plus 1 over 2 plus 1. Then we have the constant rule. That'll just be 4t. Now, what we have to do is evaluate this from negative 2 to 2. Notice I didn't include a constant of integration. We don't need it. We can say it's 0, right? Because all the fundamental theorem says is we need any antiderivative. Well, setting the constant to 0 is still an antiderivative. This then becomes t cubed over 3 minus 4t evaluated t equals negative 2 to 2. We'll get 2 cubed over 3 minus 4 times 2. That is the evaluation at t equals 2. Then we have to subtract from this negative 2 cubed over 3 minus 4 times negative 2, the evaluation when t is negative 2. Look what we get then. 8 thirds minus 8. This term here is negative 8 thirds. So minus negative 8 thirds becomes plus 8 thirds. Then we get this term here is plus 8. So it's minus that. It's 16 thirds minus 16. And that evaluates to negative 32 over 3. So this integral evaluated out to negative 32 over 3. Next, let's look at evaluating the integral 1 to 9, x minus 1 over the square root of x dx. One of the techniques we learned is if the denominator is a monomial, we can divide each term in the numerator by it. So this will become the integral from 1 to 9. X over root x is square root of x, which is x to the 1/2 power, minus 1 over root x is x to the minus 1/2 power. Right now, fundamental theorem says find any antiderivative, power rule. X to the 1/2 plus 1 is x to the 3/2. Then divide by 3/2 is the same as multiplying by 2/3. X to the minus 1/2 plus 1 is x to the 1/2. Then dividing by 1/2 is the same as multiplying by 2. That's our antiderivative, so we evaluate that from x equals 1 to 9. And we get 2/3, 9 to the 3/2, minus 2 times 9 to the 1/2. Then subtract from that 2/3, 1 to the 3/2, minus 2 times 1 to the 1/2. Square root of 9 is 3. Cubed is 27. 27 over 3 is 9, times 2 is 18. Minus, square root of 9 is 3, times 2 is 6. Then we get minus 2/3 plus 2. This evaluates out to 40 over 3. Let's now evaluate the integral from 0 to 1, x squared times 1 plus 2x cubed to the 5th power dx. There are two ways to go about this. You could certainly expand out 1 plus 2x cubed to the 5th power and then distribute an x squared through. I won't stop you from doing that. I don't want to do that much algebra. So what I'm going to do is I'm going to say, well, let u be 1 plus 2x cubed. Then this would mean that du is 6x squared dx. Now if we look, we have a dx here, we have an x squared there. All we're missing is the 6. So if we multiply by 6 and then divide by 6, we'll be fine. We'll have now our du. So what this becomes is 1/6 the integral, and I'll worry about bounds later, of u to the 5th du. Now for our bounds. We take u evaluated at 0, then we take u and evaluate it at 1. So this is 1/6 times the integral. When u is evaluated at 0, we get 1. When it's evaluated at 1, we get 3. right? Notice all we did was take the lower bound, plug it into u. That's our new lower bound. Then we took the upper bound, plugged it into u, and that was our new upper bound. This is 1 over 36 u to the 6th. That will now be evaluated. U equals 1 to 3. Right? We get 1 over 36 times 3 to the 6th power minus 1 to the 6th power, which is 1 over 36 times 729 minus 1. When everything is said and done, we get 182 over 9. Let's now look and evaluate the integral from 0 to 1 of x e to the 4x squared plus 3 dx. A clearer example of u sub I have not seen. We let u be 4x squared plus 3. We let du then be 8x dx. We need an 8, so we're going to multiply by 1/8. Then we have the integral, u evaluated at 0 to u evaluated at 1, of e to the u du. That is 1/8 times the integral. When u is 0, we get 3. I'm sorry, when x is 0, u is 3. When x is 1, u is 7. So we're left with 1/8 e to the u evaluated from u equals 3 to 7, which is e to the 7th minus e cubed all over 8. You could also factor out an e cubed, but it's not really mandatory, so I'm just going to leave it like that. And that concludes this video on the fundamental theorem of calculus. In the next video in the lecture series, we will look at an application of the definite integral known as net change. I will see you all in the next video.